Thanks, indeed. The thing that has us together is most generally thinking about continents. And if I recall the name of the summer school correctly, the formation and destruction of continents. The word formation and destruction are both what I would call action words. They imply change, things happening, exciting things. I'm not talking about any of those initially. I'm talking about actually stability, and I want to get us thinking about stability. The word stability implies, as it should, things not happening, things being quiet for a long time. And I actually want to think about the sections of the continents, cratons, that are quiet for a long time, billions of years, 2 billions of years. At this point, you're thinking, wow, this is going to be exciting. I have now dedicated an hour and a half of my busy day to think about why sections of the Earth do nothing. I'm a human being, too. I'm a human scientist. I know we're drawn more to questions of why do things do things versus the questions of why do things not do things. But keep something in mind. In this case, they're related. Very much so. As we're thinking about what provides stability to cratons, something we'll want to define in cratonic lithosphere, implicitly we're also asking ourselves or putting ourselves in a position to address the question of what might allow these sections to go unstable. Or if this factor changes, what happens? Now that we might get to near the end, and that is more in terms of cratonology, become a recent issue. And it's become a recent issue because we have evidence, and I actually like this image because it isolates the North China craton, that there are sections of our planet that over a long portion of time behaved like what we think cratonic lithosphere should do, stable, doing nothing, and relatively recently, geologically, and relatively quickly, they lost something that allowed them to have a lot of action and be destroyed and changed. What allows for that is an interesting issue. What it's telling us about our planet is an interesting issue. And if you like mangling things more than you like preserving them, keep them in mind. Implicitly, we'll want to address that as well. Fair enough. We've heard the word craton. See, instability. We've heard the word craton used a bit. No one jumped up and said, what is a craton? So I'm assuming you all know that, but I'm going to bore you, and I'm going to actually go through a little bit more of the definitions here. And it's a multifaceted definition as it's used by most people these days. So let's go with our own continent. And this is an image from a paper by Hoffman. It is, in my mind, a beautiful scientific image. If this is the first time you see it, take a few seconds to process it. Take it in. That's a few seconds. I've added a little bit of color. Hopefully I haven't damaged it just to help you visualize it. If there's one slide you take from my slides, take this one. It's so information rich. So information rich. I suspect I'm not the only person who's read this paper. I am? Really, that few? So everybody agrees it's a nice light read, right? It's about that thick. When I started as a graduate student, I was interested in cratons. It took up half the first folder I had of papers. It's worth a read. It's worth a read. But I actually like this picture from it. It's a picture that always reminds me every picture tells a story, and this one tells a beautiful story. And in fact, let me give you the title of this paper to see if some of you have what I call a gestalt moment. You've processed the image. The title of the paper is The United Plates of America. You don't even have to read it. The title and that's a lot of what he was saying. And it's interesting. Barbara, who I see is not here, thank you, Barbara, mentioned yesterday, right, a little bit about this, right? That's one of the main arguments here. You got this terrain, right? We don't think about that as a separate plate today, but in the past, maybe it was some separate section. You got this terrain. Rick talked a little bit about this. In between this welded trans-Hudson origin slammed together. That's the argument. It's a geologic argument. That's how the core of the continent formed. Around that, you have younger regions, Grenville origin and orogeny. Orogeny we don't think of as stable. And this is already telling you stability. We have to think about time issues when we actually define that. Appellation. Archean Proterozoic. Now we can start thinking about things that geologists did historically, what we mean by stable. And the number here is arbitrary, just so you know. But we can say, let's define, so we can talk to each other, stable section is something with no major tectothermal events, tectonic event, orogeny, rifting, thermal, a lot of volcanism coming through. We'll let one or two go. And if I say 2 billion years, I'm kind of ruling out the Grenville, the Appalachians, certainly the Cordillera, certainly the Laramide, sorry, Gene, certainly the Basin and Range. Those are not the stable sections. Those are the active sections. And with the power of graphics these days, you can just draw this on yourself. You can say there is what I'm going to call a craton. You can then go to a glossary of geology, which I did, and find this definition. This is the oldest definition of craton. It's a geologic definition, a part of the crust which has attained stability and which has not been deformed for a long time. I'm glad some people giggled. That definition does make one giggle. It makes one giggle because it seems like a squishy definition, not precise definition. As scientists, woo, we love precise precision. But keep something in mind. If we get too precise, we can lock in our thinking a little bit too much. Sometimes it's good to have a little wiggle room in a definition. And this one allows it. If you want to add an adjective, Archean craton, feel free. You don't have to. But we need to be on that page first. And, hats off to the geologists. Hopefully there's some in the room. That's a lot of work getting there. Think about the work in just creating a map like that. So no tectonic disruptions for billions of years. At this point, you'll actually see that putting continental craton on this becomes oxymoronic. There's no oceanic lithosphere that old at all. It's geology, and it is a definition in terms of, and we started to talk about this, it's a craton, the mantle is the crust. I'm not saying it's right or wrong, but originally it's in terms of the crust. Since Don Anderson is coming later, I pulled his image here. I could have used others. You'll notice here on this map, there's these little numbers in yellow indicating approximate seismic root thickness. This is now coming from a different specialty, from seismology. The word lithosphere is a loaded word, just like craton. We'll get there. I will just let you think about what you think lithosphere is, and then we can come and discuss it and see if we're on the same page. Here's an example. You might notice I'm using historical examples, not modern, because I actually want to leave the modern as modern issues, new problems we can think about. Here's an example of a seismologist doing the one and only thing seismologists do, measuring time. It's from the work of Steve Grand. I heard that yesterday, and I actually loved that phrase. I don't think it undervalues seismology. You see, actually, that fast seismic wave speeds below North America here extend to great depth, greater than in the oceans. And this has been noticed worldwide, and you've seen more modern compilations of that. If you look at the section where we see the oldest craton, the thing we defined as stable, it is associated with that deepest region. Let's just call this the seismic lid for now. That can be well defined in seismic. How you do it, that's fine. How it relates to the lithosphere will come back. And that's been noticed worldwide. So thick lithosphere, seismology, definition in terms of deep lithosphere. I am so glad Rick spoke before me, and I will mention this twice. Thick lithosphere that hasn't been recycled for a long time. Just as I suspect I'm not the only one who read the Hoffman paper, I suspect some of you know what you're looking at here, even if it's a little washed out. And it is... Yes? Big hole. Yes, it is. It is a big hole in the ground. It's a specific big hole in the ground. Sorry? It's the big hole. It's the big hole in the ground. All right, well, I should give it proper big holiness, I guess. As people, we dig big holes in the ground sometimes. This is, yeah, that's that. This is Roberta's entry point to actually going down into the lithosphere, bringing all this stuff. As people, we dig big holes, then we fill them in. In this case, it's a big hole we actually dug to mine some stuff out, originally diamonds. Rick talked a little bit about this. It's associated with a kimberlite pipe. This isn't what the kimberlite pipe would have looked like beforehand. It's us digging through it, going down, originally pulling up diamonds. That's a whole separate discussion why we do that. Let's just say we did it. We did it for various reasons, but the reasons also led to some scientific rewards. It gave us some information about our planet. And a little image here. It actually gave us probes, not the kind of probe you were alluding to that Roberta has, but, you know, I mean, really, nature's kind of kind in some sense, and we're lucky to have that. Probes into the deeper structure of the lithosphere, in that when this kimberlite pipe came up, it ripped off portions of the wall rock, brought them to the surface, xenolith. Diamonds were the ones that were most intriguing for a time, economically, certainly. Also, as Rick alluded to, there's some things that are nice about them in terms of dating. They also form under specific temperature and pressure conditions. I'm old enough to remember the old Superman movies, and there's a new Superman movie. I don't know if he crushes coal to make diamond in the new movie. Anyway, it's an indication of pressure and temperature. It gives us some indications of what's going down below our digging reach. We don't mine that deep by any means. Here is why I am so glad Rick spoke before me, because these next two slides, you won't have to hear me babble my way through what xenolith data can give you. Now, on the bad side, I told people this already, it means 45 minutes of my reading his papers last night was wasted because I wasn't sure if he was going to talk about it. But you've gotten the beautiful picture. Here are some xenoliths from various cratons. This was given to me by Sinti. You can see Sinti's a busy guy. Look at all the data he's collected there and everything. It's a review paper. It's a review paper. It's a lot of people. And it shows some consistency. I mean, there's some scatter there. But from geothermal inferring temperature and pressure conditions through specific mineral reactions. I'm guessing there's a few different thermometers and barometers that were used here, not one specific one.
They're all the same.
They're all the same. Okay, well, anyway, a specific one. If you want to ask about it, feel free. Notice that, and these are geotherms that Roberta put on. It's a family of geotherms. We're not assuming we know the temperature perfectly, conductive geotherms. But for the story I'm sort of building up toward, just notice that it's cold at depth. Cold at depth. Kent asked yesterday about, extrapolating a adiabat onto that. There it is. That's 1380. Pick your favorite mantle potential temperature. That's not a bad one. I don't think we disagree with it too much. Notice that these are at this depth. They're not at the temperature of what we consider the well-mixed mantle, the thermally well-mixed convecting mantle. We also, we is not me, we as the collective, can get age dates here. And that's what Rick mentioned. And this was what I was so glad, because actually how this works, there are a couple of steps I've come to appreciate. And I'm glad you went through it. You got it. You got the story from the source. We can actually get ages. And here's another Gestalt moment for you. Put those two together. Hopefully that's the direction you get pushed into. Seismology, the lithosphere, or the seismic lid, whatever you want to say, is thick today. This is saying it was thick in the past, 2 billion years ago. And that's interesting. Definition in terms of, and I've snuck something in here now, in terms of a buoyant route. Now, we can get that a couple of different ways. You can actually look at the stuff that comes up, interrogate it, say, how does it look chemically relative to what we might call reference mantle? And it looks depleted. It looks like it would be buoyant. There's another aspect that came into this in terms of this definition. It was from geochemistry, but it also ties into a definition based in terms of a synthesis, a collective of all these things. The person who came up with the synthesis is not in this room, so I can say it now. It is a great synthesis. It is perhaps one of the greatest syntheses in earth science, in collecting things together about a particular region. And it still casts a very big shadow in our thinking about cratons. Now, with that due proper respect, I'm going to walk us through rather quickly how I think the person got to that synthesis. But it wasn't trivial. Once we see it, we take it almost for granted. To show you one other data set that does come into play, Claude Jopard will talk more about this next week. This is a heat flow map from our continent, compiled by Jean-Claude Maréchal, Claude Jopard, and their students over long stretches of time. I've realized I put up something that should irritate Thorsten. Why does this irritate you, Thorsten?
It's not done right.
I think it should irritate him because actually when I see heat flow maps, I always kind of insist that you put in little white dots that tell you where the measurement point is to see how well sampled your region is. This one doesn't have it. We take advantage of wells that were drilled and put in, boy, I'm going to sound so non-technical, but it's not too different, thermometers down to the depth and try to actually infer temperatures and heat flow coming out. What I will say, actually, if I were to put in the white dots, this region, the North American Shield, and Claude will correct me if I'm wrong, is the best sampled in terms of continental heat flow data, the points we have wells, in the world. And that's why I chose it. It's the best one to do this. Over here, be aware what you're seeing. If I were to put in the dots where we have heat flow measurements, a lot of these circles, you'll see one well. So keep that in mind. But for the cratonic regions, we've got it pretty good. And there's less heat coming out of the planet. Remember, seismic lid here. I don't know if it was a choice to choose blue and blue to make your eye think cause, but there it is. It's historical. Those are the color palettes we've chosen. Remember the stable portion. Now we can come back to something the person who came up with this synthesis in terms of cratonic structure had to deal with. What do we mean when we say lithosphere? The reference model, I will go as with the ocean side, a very simple cartoon of the oceanic lithosphere. A mid-ocean ridge, decompression melting, crust forms, material moves off the ridge laterally. It cools, heat is lost into the ocean, ultimately off into space. As that material cools, a conductive boundary layer forms. This is that thermal and upper boundary layer, the thermal boundary layer of mantle convection, down to some well-defined, well-stirred mantle temperature, 1350, 1380, those are close. That's a thermal layer. When we talk about plates in lithosphere, traditionally we think strength, but the idea going in, when people started thinking about cratonic lithosphere, was that this is also a region that is cold, you're near the surface, and rock properties, Greg Hirth will talk more about this, but I'll just give the one that there's very little debate about. The viscosity of rock, its resistance to flow, depends very much on temperature. Colder rock is more resistant to flow. Its viscosity increases, and it increases exponentially. A good rule of thumb to keep in mind if you don't is every 100-degree change in temperature is about an order of magnitude change in viscosity. So where exactly you say it becomes strong enough to resist geologic loads over geologic time, you would define as the mechanical portion of that boundary layer, or the plate, or the lid. And we knew that from oceans going in. We can extend this out right into the continents and right into the craton. And we also know here in these regions, we have oceanic heat flow data where it's thicker. The heat flow is lower, we know that. And we have low heat flow here from the continental cratons. We have this thick seismic lid. We can say maybe we just extend this out and this is what we're seeing. And if we look at some of the xenolith data, you say, well, it's consistent. Yeah, it's cold down there at that depth. Makes sense. This is a summer school, yes? Anybody? Yes? Yes? Okay, good. Pop quiz time. You were all here yesterday. You all saw Meredith's fine talk. Thank you. You all know, if I were to give you a pop quiz, what the problems are, if this is the interpretation you stick with. I'm not going to pass out the quiz. Take it in your own mind. Also, keep something in mind. The way I'm using the word problem here doesn't mean a bad thing. Problems can be a good thing. If some idea we have about how the Earth works leads to some prediction that doesn't match observations, we'd say that's a problem, yes? But it's a good problem, isn't it? It's telling us something. There are none of my students here that I see, so it's good I won't bore them, because they get bored of me saying this. Knowing what the answer is not is knowledge. Knowing what the answer is not is knowledge. That's not the answer. Meredith told you that's not the answer. Why is it not the answer? What's the problem? I'm not going to do that.
cold, so its density should sink.
Yes, that's right. Isn't that one of the things that made us really accept this model of the ocean side? The ocean floor gets deeper and deeper and deeper. It's cold, it sinks. This is really cold. Maybe this should actually sink below, if you did it, sea level. And of course, everybody who lives in Canada, in the center of Canada, knows you're below sea level, yes? No, you're not. Topography, there's the gravity, the associated gravity. Now, I'm actually mentioning these because these are observational problems, not the other problems that you might have thought I would have jumped to for anybody who knows what I do, the quote-unquote theoretical problems. That's not as hard a problem. Can't be. You already know the answer to this problem, what you're going to do. First student who grabs me after the talk and tells me what I am referencing there, I will buy a beverage of your choice tonight. That's a quote from something. That's where the synthesis came in. And the synthesis comes from Tom Jordan, and we've heard a little bit about it already, the tectosphere idea. That really what you have to do is if you're going to make this work in terms of the other data sets, gravity and topography, is have some depleted residuum. Words for this change. This is what I grew up with. Hopefully it's still okay. Something that is chemically buoyant relative to reference mantle, maybe not as buoyant as the continental crust, that compensates for this cool temperature in terms of the density here, so you don't sink below sea level. That's the essence. Pulled right from a classic Jordan paper. If you haven't read one of these, and you know I'm not fooling you when I say it's one of the great syntheses in the history of our field, please read one. Several of them are very short. There's a conceptual cartoon, and really it's the conceptual. The depths about these are open research questions. These are the things we want to argue about. But conceptually, this is the idea that you have low density crust, then you have this root, you have a temperature profile that we can now match with some xenolith data, even better than in Tom's day, the thermal boundary layer. We have now, and this is really where the use of this came into vogue in our field, the chemical boundary layer, if you like, chemical lithosphere, chemically distinct from reference mantle. That really wasn't talked about for the ocean side. That's changed a little bit. And somewhere in there, this becomes a little bit more debatable, and it's some of the things I want to talk about, the mechanical boundary layer. That's the model. Okay, I've gotten us there in 20 minutes. That's good. We need to be on the same page. This is, I think, a decent definition of cratons and cratonic lithosphere, observationally based. Notice there's issues of stability, issues of longevity. Now, at this stage, hopefully, you've processed all this. You're in a point to start asking your own questions. What is it you might want to know about cratons and cratonic lithosphere that's not in here already? What question jumps into your mind? And just do it as an exercise. I'll open it up for discussion in a bit. Also, as you're doing it, and maybe it's not a bad thing, right? We're supposed to find research problems down the road. Think about that. Ask yourself, and this might tell you what leaning you're toward, what tool in our scientific arsenal of tools you would use to address the question. Would it be seismology? Would it be geochemistry? Would it be petrology? Seismologists, what's an interesting cratonic question that's not resolved today? How thick is thick? That we talked about that. I said I dotted the issue. I said seismic lid. I don't know how you guys define seismic lid necessarily, but yeah. How would you address that? Good question. Let me add one. Same thickness everywhere? In all cratons? In back? Yep. Yes?
Why always velocity variations from the seismology may not fit what composition will...
Ah, that's a good one. Yeah, can we pull out the composition from the thermal and the seismic? Great question. Or, when Roberta defines it, why is it different than, I don't know, let's say when Richard defines it? Seismic chemical definitions, great, coming into petrology. Can anybody think of a question that comes into your mind that would not be addressed by the tools of geology, geochemistry, or seismology that's interesting to cratons and cratonic lithosphere?
This newfangled geodynamics.
Well, thank you, Thorsten. Yeah, there is this newfangled geodynamic stuff. Yeah, there is. There are some questions that come to mind that are geodynamic questions. For those of you who don't know me, and it's good for students, right, to get to know people if you want to talk to me at lunch, I am a geodynamicist, and when push comes to shove and I am asked at some scientific institution from a scientific side, Adrian, what is it you would say you do here? I usually say I do this. That's it. That's a model. I construct models. We've heard the word model thrown around quite a bit already. No one got up and asked a question I would insist people ask. What's a model? Let me ask a more direct question. Does anybody consider themselves not to be a modeler? Really? With all due respect, those of you who raised your hand, I completely disagree with you. Completely. You're modelers. 100% you are. The fact you got here today tells you are modelers. Here's an obvious statement. The world's a complicated place. A lot can go wrong in getting here. Over 3 days, I'll speak for myself, I have a model of what would happen when I got here. I'm going to go to Pete's, I'm going to get a cup of coffee, I'm going to walk over here. A lot of other things can happen. The real world is very different. I have that mental model, it's in my head. A lot of the frustrations we feel in life, quite honestly, are when our mental models don't match reality. What do you mean the espresso machine's broken? My life is ruined. Now, this sounds funny, but actually, scientifically, it's similar too. I'm going to pick on Roberta. There's no way you're not a modeler. You have a model in your head right now of what cratons are. I know, that's what I'm saying. What is a model? You're defining it wrong. What is a model? No. Now we're getting into definitions. Why don't we get too precise about definitions? It affects our thinking. That's a mathematical model. That's not what all models are.
A model is a way to represent something. For example, geodynamic or...
Good. We're getting there. Is it the thing itself?
No, it's not the thing itself.
It is not the thing itself. How is it not the thing itself?
It's less complicated.
Yes, that's exactly right.
Except Dorson's.
Well, now we're getting into the issue of good versus bad model, but that's a different thing. I'm not even going to say it. We're joking. If forced to, it's a simplified representation of something, okay? Now, here's a harder question. This one's loaded. Why do we make models? Right? Who cares? There's the craton, there's the seismology, there it is. Now, I understand seismology has its own modeling in it, so I have to be a little careful. But why? What's the point?
Mental calibration.
Sorry?
There's a mental calibration.
Mental calibration. Ah, yeah. I like that one. None of us are as smart as we sometimes think we are. Our brains are limited. We can't process all that information. That's why you make mental models, right? That's why you simplify things. You can't hold all that. And usually we think about what we think is the most important things. Is that a fair statement? We want to get rid of some of the complexity we think isn't quite as important. Understanding, maybe. Prediction, maybe. There's a range of things, but we do. Keep this in mind. Simplify. You do it all the time. Now, the modelers in the room might realize here that I'm actually trying to defend us in a little bit of a certain way, because actually the criticism one can always level at modelers, any modeler who's standing up here, is, oh, you've oversimplified, or oh, what if you put in this, or oh, what if you put in that. It's not a bad criticism, keep that in mind, but right, by definition, a model will do that. We're looking for as simple as possible, but no simpler, as a greater scientist than myself once said. How do we get there? Now, I could babble and I could give you more and more abstractions about how to do modeling. For those of you who are instructors, you know sometimes that's not the best way. The better way for some things is just to walk through some examples. So I'm going to walk through some examples about models related to cratonic lithosphere, some historical ones. Anytime you construct a model, and I will speak for myself as a modeler, you sometimes forget that even before you sit down to pencil and paper, before you write differential equations, before you put differential equations into computer, you're implicitly framing the question. You're formulating it. You're saying, this is what I want to think about, this is what I don't want to think about. So if we think about this question, let me pose it. It's a geodynamic question. We saw some of those properties. What is it? What is key to allowing a craton to be a craton? The longevity and the stability. Is it the buoyancy? Is it in the root? Is it in the crust? Is it the strength? That's a great geodynamic question. That's one I wrestle with. Many people wrestle with. But we frame it. I've been sneaky. I snuck in a cartoon. That cartoon is actually framing something very specific. Cartoons are models, by the way. They're simplified representations. And they can sometimes be the most powerful model in directing thinking. Be aware of it. Think about your own thinking. What can we do from this? We can actually get to this conclusion if this is the way the problem is framed. I'm actually going to say that stability and longevity are no problem. We would completely understand it if this is the way we frame the question. Why do I say that? Well, it relates to what Tom Jordan did in the great synthesis he did. He said, well, let's consider some reference column. Reference mantle. We want a reference to things. Let's go down to mid-ocean ridge. That's the easiest place. Let's consider within cratons regions that are stable, thick, long-lived lithosphere, doing the same exercise. Meredith talked about this. You can be more precise. You can add the equations. I'll just do it conceptually. Say, what is the density here relative to this one? And we can compare the two. Why would we do that? Any students, if we're interested in longevity and stability, why would we do that? Should be equal. What if this one is somehow more dense relative to that one? What might you expect to happen? Yeah. Sinking doesn't sound stable, does it? No. That might be why you do it. That's what Tom Jordan did. Now you can actually say, okay, what if the density of this column is the same as the density of this column on average? I can actually use a word. I can say when I talk to my friends, they are the same density. And then you can say, no, I think I should say that in Greek. And you can look up the Greek equivalent and you say it's isopycnic. That's what isopycnic means. Now you can also say, what if I'm strict isopycnic? That I say the density right there, the density right there are equal. That's strict isopycnic. Satisfied? Yes, no? What if I tell you, and let's do it, they come out to be the same? Problem solved? I'll let you ponder it. If this is the model, and you say, okay, that density is the same as that, I have now explained cratonic stability and longevity, and you got an hour.
What about secular cooling?
Okay. Secular cooling. Let me tell you can do this another way. Tom Jordan did it this way, it's related. Shiji talked about Rayleigh numbers. You can actually do a local Rayleigh number analysis, local within the craton. And in general, a Rayleigh number will always express something that drives motion, in this case, density variations in the field of gravity, relative to things that resist motion. Viscosity. Material can, want to move under density, but it can be so strong that it resists that motion. And smoothing, if you smooth away the density variation. And I won't give you a pop quiz on Shiji's talk, but you already know, right? There's a ratio that allows for stability when you do this local analysis. Yes, an equation comes into it, but conceptually you can do it this way as well. I'm doing the science, but I am trying to, give a little bit of tutorial. What can I tell you in terms, if you don't do scientific differential equation modeling, something you should do is you read modeling papers, which I'm sure you all do. Question 1, what's been assumed? Always. What have I assumed? I've snuck it in. I've done it on purpose, because sometimes it is sneaky. I've assumed it's a fluid, fine, yeah, viscosities. I've assumed something about the rheology, the flow properties. You might quibble with it. What else have I assumed? Let me ask you this. What's implied? Time scale. Somebody should be able... Sorry? That is representative, yeah. All are the same somehow. Time scale. What's the other one that you might want to jump in? If somebody says time scale, you say odds are you're going to be right. Length scale. What length scale hasn't entered at all? I can define a local Rayleigh number right down there without talking about the extent of a craton at all. Doesn't even come into it. And if you say the local Rayleigh number analysis says, yeah, it's stable, that is telling you that a 1 kilometer wide craton is just as stable as a 100 kilometer wide craton as a 1,000 kilometer wide craton. That should cause you a moment's reflection. It's not in there. Not a modeler. I make these simplifications. I do them all the time. It's not in there. Let me ask you this. Would you agree this is actually what you've shown if you do this, either in density balances or in local Rayleigh number? The lithosphere won't spontaneously sink. Isn't that what the analysis gives you? It is. Does that make sense? Yes? Is that all we worry about? Continental origins, right? Deformation. Do they form because that section of the crust spontaneously exceeds some local Rayleigh number and sinks? No. Why? Why do they? I'll open it up to the professors in the room. Things are moving. Implicit framing of questions. This cartoon is nasty. Nasty. Nothing's moving. You're saying, oh, this goes up and down. Is that the case for continents? Come on, plate tectonics. They're drifting. They're moving around all the time. The mantle's not static. It is... Dynamic. That's right. I'm doing my best to be interactive with you. You got to play along. Let me come back to it. Look at these observations and let me ask you now something else. Are these interesting observations?
Yes.
We have a yes. Thank you. I say no. Who's right? Thorsten. Why do I say no? I've actually been careful how I write up these observations. No tectonic disruption, thick lithosphere. A little planetary science for you. Some planetary scientists might argue with me on this, but I hope not too much. If we lived on Mars, Venus, or the Moon, what we call single-plate planets, planets without plate tectonics, one plate, these observations would be the planetary norm. They would reflect the general state of everything. The lithosphere on Venus hasn't been recycled. It's been sitting there about 1 billion years for sure. Not a lot of tectonic disruption. Why are these observations interesting for sections of our planet?
Most of the planet doesn't behave that way.
Exactly. That's the real interest in cratons. Sometimes we forget that. Sometimes I forget it. I work on cratons. I forget it. That's what makes them interesting. The observations are... Thanks for playing along. I'm not picking on you. I did this to...
Now you agree with me.
Now I agree with you. I did it to set it up. It's a setup. I've set you up. They're interesting relatively. And as a modeler, once you actually say they're interesting relatively, you've got to say, okay, maybe I need to move out of a local framework to address this question. These aren't the questions, and I'm going to tell you this is not a subtle difference in how modelers frame models. Boom and boom. Those are the proper questions in my mind from a modeling side. If you just do it locally, you can reproduce what Tom Jordan did, what a lot of people did with critical Rayleigh numbers. You'll get the same conclusion. That's great. It's worth going back and doing that, but that's it. Cartoons are models. That's clear to me. I will tell you right now, this is less clear to me. In a dynamic mantle with things moving around, Rick talked about cratons slamming into each other. In tectonic settings, what provides the stability? What's the buoyancy? All these things. This, to me, is not as clear. Within a dynamic mantle, and that's been the more recent, for my field, geodynamics, the more recent type of modeling that's gone into addressing the craton problem. It's moved to thinking about it within the context of a dynamic mantle. You'll notice I'm being a bit of a devil's advocate, and I'm not doing that in any ego sense or anything like that. I'm doing it to say there's still interesting problems here. We can say, okay, well, cratonic lithosphere is cold, so it's strong, high viscosity, that makes it stable and long-lived. Sounds reasonable? Yes? Yeah? Okay. Back to Jim's question. Keep in mind, same thing holds for old oceanic lithosphere. Temperature dependence and viscosity is very high viscosity. I can do, or you can do, go do it. You can do a local Rayleigh number analysis for oceanic lithosphere. Get its density. Its viscosity, if you say viscosity is the only thing involved. And you will predict it'll be stable and will never subduct. Is that a good prediction? No. No. Already what Jim's telling you, or did tell you, maybe just thinking ductile viscosity. Maybe that's not enough to understand the planet. Plate boundaries form. Regions of localized deformation. Greg Hirth hasn't spoken yet. We'll have a rheology discussion. We don't understand completely what goes on there. I will grant you, but faulting ductile shear zones. Does that apply to continents? Do we care about faulting in continents? Anybody? Field geologist? Yes? No?
People who live in Berkeley?
Thank you very much. Yes, the same would hold for continents, right? It's not just flowing. It's not just viscosity. Continents deform other ways. We need to think about that as well. Why don't cratons do that? It's not just a matter of they don't flow, they don't fail, they don't fracture. Well, it's dry. Maybe that makes it stronger somehow.
They would fracture it to become a large meteor impact.
Meteor impacts could break it. Maybe, yeah, why not? Early Earth.
Break it up.
Keep in mind this dryness issue, right? Herth and Kolstad have told us, and thinking about the oceanic lithosphere has changed as well. There is talk of chemical or dehydrated component within it as well. So it's also dehydrated. It's also lost water. And the last one is chemically buoyant. Good plate tectonicists know this, so are some sections of young oceanic lithosphere that are subducting. They're attached to older slab, that's true. So, before you're too quick to say, well, it's cold, dry, depleted, well, you've got to be careful. Does anybody want to say anything before I move on? It's kind of a natural break. Yeah, the thickness. We'll come back to that. That's actually something I want us to think about, and I'm glad you jumped on it. Because then you're saying maybe the key is not this buoyancy, just the buoyancy, or maybe it is the thickness. You've touched off something I wanted us to end with, but that's great. I love it. If it is, then doesn't the question become?
Why is deep?
Yes. And if that's what we go with stability, I told you stability is going to tie into all these action words, formation, destruction. That ties into formation. What controls its thickness? Let me throw out another one. Time. Has the thickness always been what we see today? Maybe not. Good. You're playing along good. You're getting there. You're getting there. It's not a trivial problem, and I don't want us to think it is. In fact, one of the things I'd like you to come away with.
That's where you are, though.
What do you mean?
If a craton sits very far inland, no subduction, nothing will affect it. It's going to stay safe.
There goes my conclusion, too. Yes, exactly.
It depends on whether it's on the hanging wall or the footwall as well.
Right.
You guys are great. So right? I'm not going to give you an answer. I'm actually going to go through and give you some various things that might work. That one might work too. I think we can't rule that out. If you do accept that one, think about this, and I want you to remember this. Can you do a local analysis to get that? No. It depends on what's next door, if that's what you're saying. You have to actually consider the whole framework.
Can you do an improved local analysis that includes the thickness and the length scales by means of a Rayleigh Taylor?
You could, yes.
And then also somehow modify the time scale to include for like the conics. And you're still going to be wrong. But you're going to be less wrong. And then you know how important left, right, slab, no slab is.
Mm-hmm. Yes, you can do that. You can. And it would involve a modification on that reference model. And I've taken you through the reference model just to give some sense of it. And there's nothing wrong with the reference model. It sets us up to add other things, other complexities. You can do it that way too, yes. Any other questions because I'm actually going to move into, I guess, some of the more modern modeling related to cratonic stability. This was a lot of history, yes.
I just have a question that we don't necessarily have to discuss now, but I'll bring it up, which is where does the strength reside in the cratonic lithosphere?
Brilliant question.
Some people say it's the mantle lithosphere, other people say it's actually in the crust.
I'm going to address that.
So I guess even for stagnant convection, there is the mantle is still convecting.
Yes, it is.
So it's still a dynamic mantle.
Yes. Yes.
So I guess here the dynamics, you really mean like plate tectonic.
I really do mean, yeah, our planet, and that's why I wanted to say relative to our planet. Yes, I do mean plate tectonics. But I also do mean other things that have come in, and we'll talk about this, that are somewhat related, that are more specific to our planet. And Rick was talking a little bit about this, recycling of continental lithosphere, delamination, these types of ideas as well. Whether those would operate without plate tectonics or not, I don't know the answer to that, but I also want to talk about those.
I think we have to consider, can we break a craton? If you look at the supercontinent cycle, some Archean cratons may have been broken.
Yes, rifted.
Yeah.
That's not stable.
No.
You're already hitting at something I want to come back to. Do not confuse longevity with stability. They might not be the same thing. They don't have to be the same thing. I'm not going to name names, but in the literature, people fall into this trap. Just because I keep it around means it's stable. That's not necessarily so. Well, there's many ways. Thorsten mentioned one. I actually walked my way through what I tried to walk you through to do some cratonic stability and longevity modeling. And Louis Muraci and I developed a model, and I want to talk about it. It's one specific one. And what's different, what you're looking at here is, this is a mathematical model, Roberta, but it's the conceptual that's important as well. There is a convecting mantle. These tones are cold, an analog to oceanic lithosphere here. This is hot, convecting through. We have a temperature dependence in viscosity. We have to allow plates to be strong. And this comes back to Shiji. Let's just say I do want to think specifically within the context of plate tectonics. That's not a bad way to think about it. I need to have some model analog for a plate. I'm going to put in a continent. It doesn't have to be a craton. It's a model continent. It has crust. Keep in mind, this is the most buoyant stuff we can think of, more buoyant than the root. Chemically light material. It can have its own rheology, its own viscosity, its own flow law. I can put in the root. I can vary its density. I can use Tom Jordan's numbers. I can use anybody's numbers, but we can just vary it, just see what we need to do. I can define the base of a thermal lithosphere, a thermal boundary layer here. We need to do that. You'll notice it's thicker in the continents than the oceans because there is some stability being brought in by the continent itself. Talk a little bit more about how this is initialized. And there are these failed regions, an analog to a mid-ocean ridge, here a fault zone, here what I will tell you in this model is going to be a décollement for the people who like to deform continents. Regions where localized failure kicks in. This is actually described by a multi-valued rheology. If stresses exceed a critical level, a level I is the modeler, or informed by Greg Hirth or somebody who studies rock deformation, says rocks break or go into ductile shear, localized deformation. And I have to prescribe that. And I can do it differently for the crust, I can do it for the root, I can do it for the mantle. But I want to get this analog to plate tectonics, to the ocean side. How did I set this model up? Here's what I did. I started with the continent in a convecting mantle, moving around dynamically, and I told this a numerical code. I told the code, do not let the continent do anything other than translate this way. Don't let it deform. Why would I do it that way as opposed to just smacking the continent into a convecting mantle? This is a bit of a more technical question, so if the modelers want to answer, feel free. Why wouldn't I do it that way? There's no way I would start anywhere near isopycnic. The system would be completely out of thermal equilibrium. The boundary layer here wouldn't have had time to grow through the continent on that side. And another way of saying this, the system would go through a complete transient. It might be overly dependent on that initial condition. I wanted to let it go long enough that I could develop this cold boundary layer. Now remember, that's higher viscosity. I want that to see if that's what's providing stability. That's why we did it that way. And then once the model, and you had to run it, this takes a little longer to run, it's a little more time intensive. Once the continent was coming into a model subduction zone, I let it deform. I let it do what it wants to do based on its constitutive law, based on its buoyancy. Something else to think about when you do models, always, or when you read models. Ask yourself how many, ready for a jargon word, free parameters are in the model. Does everybody know what I mean by free parameter? Things I don't know the exact value for, that if I'm a good modeler, I do a sweep to vary it to see what it does. Crustal density, maybe we know that pretty well. Root buoyant, maybe I don't know that as well. I'm not completely in the dark, but I want to vary it. Viscosity, water, I want to vary it. I think this is, for me, maybe it's not as simple as possible, but it's close. But you can see already there's a few free parameters. And sort of tipping off these discussions, why did I come to different ways to stabilize roots? Well, this is it. Which one's correct? That's something I'd like us to talk about, because we want to say what different predictions do these different things make. Does that make sense? If you ever see a modeler come up and they have an hour and a half to talk, and they only talk about one or two models that quote unquote worked, ask them to leave the room. Seriously. I'm going to show you a lot of models that don't work. So a lot of them don't, in the sense of stabilizing things. There's knowledge there. Well, let's consider the reference model. This is the surface velocity field. So you notice, right, there's no internal deformation here within the oceanic analog to a lithosphere. Oceanic plate, I'm capturing that. Here for this region, here we're starting to get some deformation. That's the reality, if this is the game you're in. Free parameters, I got to map this out. Now I'm not going to, I should have said this. All right, let's walk through each one of these. Let me tell you this, the majority don't work, in the sense that the majority of parameter space doesn't allow you to stabilize a lithosphere. Now on the Earth, it's there, it's stable, so something's up. And again, this comes back to why are they so interesting? Because they're not like the rest of the Earth. That's important.
Is this crustal sliver just going to take off?
Sorry?
Is this crustal sliver just going to take off?
Well, let's see. Do you mind?
No.
Won't? Yeah. It does. Hopefully Gene's awake. Yes? Yes?
Sure.
Does that look familiar in your world?
It's Western US.
Yeah. Stability, instability, we get both. Here's the cartoon of what is being represented here. I chose this reference for a reason. I'm hoping this looks familiar to some people who model continental tectonics. Oceanic, subducting continental, mantle, crust, detachment surface, décollement if you like, retro shear. Who's familiar with this? Come on. No one? Really? One person? I don't believe it. Okay. It's not new. It's classic. Beaumont, Willett, many people who study origins, orogenic orogeny within continents have been modeling this situation. Doubly virgin origin belt. Deformation of the crust above a subducting region. Subducting continental region, right? That's continental crust. That's continental crust. Models for Tibet. I'm not saying they're right or wrong, but models for Tibet are based on this. Models of other origins are based on this. Localized deformation, Thorsten's crustal sliver. That's what's forming. Now, we've reproduced what's already there, but it's deforming. Also, right, if you give up the notion that continental lithosphere, and all continental lithosphere is actually chemically distinct from reference mantle. It doesn't have to be under a craton. If you give up the notion that that can actually subduct, then you better forget about talking about delamination. Sorry, Thorsten, sorry, Gene, because it wouldn't happen. If you think it does, you're already saying that, yeah, well, maybe buoyancy is not the only issue. And it can. And it detaches right at that surface. That's that reference model. There you go.
Buoyancy number?
I'm going to give you the exact numbers in a bit, but let me give it to you now. If I say the mantle is 3,300 kilograms per meter cubed, I'll give it to you in real numbers and I'll show you buoyancy ratios. The crust here is about 3,000, and the reference here for the green stuff, the root, 3,180. But I can vary that. You will oftentimes hear, I'm not naming names, people can just nod if they have, this phrase used in cratonology. Has anybody heard this? Yes, yes, yes. Whoops. Come on, Adrian. I didn't even have that much coffee. Feeling a little undervalued here. That's the most buoyant stuff in the system. The deformation, the décollement along the base of this, which is tied into what you think the rheology of the lower continental crust is. We talked a little bit about this. I haven't told you about it, but also I can put radiogenics in the crust. You're separating out the most buoyant part. Models that fail can tell you things, right? This is saying, okay, maybe one of the things that maybe we haven't thought about as much is, isn't it better if we keep this a package? Yes? Yeah, and that's saying the crust might be just as important, or at least it might play a role. A lot of times it's forgotten. That's why I have the crust in here.
Adrian, sorry, I don't mean to go on this, but the maximum thermal buoyancy complex, is that larger than the 150 you get? Because it seems like it should hold down so much.
Initially, at this point, no, but the material is deforming. Notice it's being stretched out and deformed. It's being deformed through being able to viscously deform. There is a term for, this is going to sound oxymoronic, and I'm sorry, mixing across a stable density interface. Michael's in the back, Mark's over there. Stable density interface means that I have less buoyant stuff, more buoyant stuff. It doesn't spontaneously sink. If you're going to mix across that, you have to do it with some shear tractions imposed through convective motions and pull the material down. It's called entrainment. And that's what's happening. The material's being entrained. Once that stress goes away, this is actually going to rise back up.
That's just too much material getting trained. And I mean, I can see you have a little bit of a different light. I mean, that's just a model. It's not happening.
Oh, no. This model, I'm not saying this is the right or wrong model. This one is not working. And you can say raise the buoyancy. You can say raise, exactly. And that's what I'm going to do.
Okay.
You can say it's too low.
But it is because it's stuck in that blue thing on the right, right?
Yes, yes. Or you can say don't get it near the blue thing. That's an option as well. Well, since we're asking about this, here's the way we can track this. I have this little dot. I can interrogate the model all the way down. I can ask what's the temperature, what's the pressure, all sorts of things over time. I can also track the extent of this region over time. And I can define a normalized root extent. Let's say it starts at 1. And then I can see what happens over time for different parameters. Does it shrink or does it not? Does that make sense? And it's a way to encapsulate the results of a lot of models. This is going to be a little bit busy. It's the most detailed result graph I have. What are you looking at here? This is a buoyancy ratio. Thorsten wanted that. It's a ratio of chemical to thermal buoyancy. The thermal buoyancy negative, chemical positive. Here I've put this in terms of reference root densities. Now remember how I track this. So there's the root, different root depths. That's a free parameter. Thickness will come into play. Over 50 million years, what's my extent? Over 100 million years, what's my extent? Now keep in mind, if the extent goes below 1, that doesn't mean it's necessarily being recycled. It could be that the craton rifts and breaks apart, and I'm only tracking it from the center. But that's still telling me it's not completely stable. If it stays coherent, that will stay at 1. That's why we chose this as a way to track it. It's just a way to condense results.
Adrian, is there a root extent where the whole thing craters?
We'll get there. Yeah, there is. Okay, so for Thorsten's, right, I'm sorry, I got the wrong reference one. That's, I guess, why it's more is going in. In this one, it won't. This is actually going to stop that downwelling. I think that's what you were asking, and that's what Jim is asking. But it's not actually stopping the deformation from occurring. And it's not going to stop, in fact, rifting from occurring, and this is just to keep this in mind. Longevity in this case does not equal stability. All right, that's actually going to rift. Mark's question, if I make it overly buoyant, the chemical buoyancy, gravitational potential energy, is this something people are familiar with for continental tectonics? No one? You have one person? I make it either too, it might collapse the other way. It might just pancake out, and that can happen too. I'm going to make a bold statement. This is based on that type of modeling I've done, but it's based on the modeling of a lot of other people. I'm not the first one. We're not the first ones who put cratons in a dynamic mantle. Duin, Shapiro, this is a PhD thesis at MIT. It's hard to get a hold of, but if you can, do. Sleep. Buoyancy alone doesn't do it. And really one of the reasons is the stability issue as well. We need something more. We need something in strength. I try to put little breaks in talks. Let's take a viscous interlude. Of course, we just took a buoyant interlude, right? Well, maybe it's the strength, right, that we want to think about viscosity. And we can even do a simpler type of model. How viscous does a root need to be to resist deformation? It's a good question, hopefully. We can do full numerical simulations, or we can do some simple scaling analysis. Various people have done scaling analysis for this. I'm going to show you one Louis and I did. At the same time, Michael and Rick O'Connell did a similar one. It's very simple. Each one, 3 lines. 3 lines of scaling analysis to make a prediction about the viscosity. The question is this, right? I got the root. Let's say I'm the mantle. I'm convecting, and I look up. How much higher viscosity does that plug need to have for me to say I can't do anything with that? I can't deform it. That's the question. Well, I'm actually going to just say what is the viscosity, right? So if I...
But the viscosity for the lithosphere, suppose it's really dry,
Yeah.
that basically it's going to be very low viscosity. You could not even try any of that stuff.
I'm actually saying deform it. But let's see what the viscosity number comes out to be.
Well, that kind of deformation is different than fluid type kind of viscous deformation. You would break it.
Exactly, but we'll get there as well. Let's start with the viscous side.
But you can't break the continental lithosphere. It's too thick. I mean, Turcotte already did that problem a long time ago when we were graduate students.
Well, you're getting back to, right, a model in your mind, too thick. That's the thickness issue. If that's what we're coming back to, then that's fine. Yeah. Well, here's the way we did this one to get a number. You can say, let's assume it does deform somehow, and calculate the energy required to deform it. If that's greater than, and this will relate to the breaking as well, it's an energetic argument, then the energy in all of the mantle, then is that reasonable to saying at that point it's effectively rigid, undeformable?
Basically, transmitted stress is not going to deform. If you have a really thick continental lithosphere, it's extremely dry.
Yeah.
So unless you hydrate it some way, this exercise basically totally meaningless.
Okay.
Sorry.
Let's finish it. If you go through the exercise, and we'll get there, you get this number. And you can test that number out. And maybe Jim already has the number in his head related to dryness. There's the deformation. I change the viscosity ratio. I get up to 10 to the 3. Let's say that is dehydrated. And then I actually stabilize it. Does that make sense, Jim? That's the argument. Yeah. But you get a number. And then you can say, okay, does water do this, for example? Make sense? Then you have the instability that you're thinking about too. Okay, to get it not to go, you have to rehydrate it. Yes? You can attach some numbers to it. One of the powers of modeling is to do that as well. I'm going to jump through a little bit in the interest of time. And Jim mentioned it. It's a thickness argument now, too. Again, here's the ratio. Let's say I put in 1,000. It's dehydrated. I have some root thickness now as well. I want to not get it to deform viscously, but I also want to prevent fracturing. Those are two things. If we exceed a critical thickness ratio here, and why would I ever disagree with Don Turcotte? I don't. I'm actually getting there. You actually become so thick that fracturing, which depends on pressure, it becomes impossible to fracture. But there is a thickness limit there, right? If there wasn't, oceanic lithosphere would never subduct, and it does. In this case, it's around there, and you're preventing a localized deformation. This one, that's the extreme dehydration. There you're preventing deformation from below, the more viscous deformation. We need to consider both, because you don't want it to rift. It's not just viscosity. That's what I was trying. I think we're on the same page with that one, Jim, yeah. That we don't want to just tie ourselves to viscosity. You want to think, we need to think about both, right? Some sections of continents do fail. They do rift. If cratons don't, and if you say it's a thickness limit, that's kind of interesting. And I already tipped us off, right? But that's one of my conclusions, that also comes into play. It's not just the buoyancy. Of course, we can prevent localized deformation another way. We don't have to make it that thick. We can just say its yield stress is much higher than the oceanic lithosphere. Some intrinsic failure criteria. Not based on pressure, but just based on chemically different in deformation. And we can do that as well. Here's a model with the craton to mantle yield coefficient ratio of 4. That's extreme. What it says is it would take 4 times as much stress to cause fracturing within continental lithosphere as it does for oceanic. So no failure. This is a little bit still of an artifact of the initial condition. That's what the one you want to look at. It's not fracturing. In this case, the viscosity is still lower, so the lower portions are being deformed in the viscous field. But you're preserving it. The other extreme, if you allow it to fail by giving it a very low ratio, you recycle. Yes? Okay. Here's the other way. Don't let it get near the high stress. Don't let it get near a subduction environment. Don't let it get near a rifting environment. Or think about the fact that most cratons are in the center of continents. Automakers consider it impractical to make drivers' heads stronger, so what do? Do they increase the strength of the head to prevent deformation? No. Something else students get tired of me saying. Strength is relative. When I did the viscosity, how viscous does it need to be relative to mantle? This is why that exercise is, I'm sorry to disagree with you, Jim, not useless. No absolute value comes into that. There is no absolute viscosity value. It's relative to the mantle, right? That's what we're referencing it to. You can buy it or not, but that has some implications. We can extend, now this is, of course, getting a little more complicated, but what if we say that the lateral, and this is a lateral now dimension, lateral variations in continents are just as important as local properties within the craton? What if I consider what Rick talked about, right? Proterozoic mobile belts. Mobile means deforming, being reactivated. And I put in a different type of crust. Proterozoic crust, if you like. Proterozoic mantle, if you like. And I let it go. I'll tell you, in this case, this is set up that if that Proterozoic mantle wasn't there, this stuff would deform. Its viscosity is not high enough to prevent it. But it's not in this case. I can let that go on the other side. And I can let that model go for a long time. Now, I told you I was going to show you unsuccessful models, and I know what that sets up. It sets up people asking questions, as this type you have, and that's great. I don't hang my hat on them. They were unsuccessful. This one is successful in a sense. It's preserving this material. You don't need to extremely dehydrate this. Buoyancy is not too bad relative to what geochemists would say. And they act as buffers in some sense. One way to think about this and the way the system is set up, the driver for all this, and this comes back to Shiji's question. I am saying it's slabs. That's what we really want to worry about, most of the deformation. When the material fails, it hits a critical stress, and it can't go over that. So the stress this region feels is always going to be set by the limit at which this material fails. And that's what buffers it internally from seeing the stress from the convecting slab. Another way to think about that, and other models that work, is to say that what if, once this failure zone forms on the edge, and this gets into more modern research, and we'll talk about it with Greg, it stays weak, so that the only weak zone is on the edge. You will also preserve the interior, merrily. That will work as well if you have a moving fault. It's an equivalent idea. What about in 3D? Okay, I showed you our exercise 300 simulations. Recently, a similar exercise was done by Misaki, doing essentially similar things, right? There's a lot of parameters. You got something you call a cryonic route. You assign it some viscosity. You say it's dry. You say it's not. You have mobile belts. In this case, WCM, weak continental margins, such as tectonically mobile belts that surround the lateral side of a cryonic lithosphere. They came to this conclusion, and it's multiple parameters, not just one thing works, that it is that WCM that provides a primary role within these models, we can disagree with the models, for the longevity of a cryonic lithosphere. High viscosity plays a secondary role. Now, that's akin to the 2D model I showed you. That is one way to do it. I'm not saying it's the way, but it is a way. And you can see the deformation over time. What's interesting from the historical perspective, people have thought about this long before me, before I was even born, actually. This is a model from Dietz. I am a friend of Australia. In terms of a way to regenerate mobile belts. You might disagree with the subduction model itself, but notice what he has here, the blue. That's the reason Archean mantle subduction starts. If you start it with this weak material that's going to become a buffer, you preserve it. That's a conceptual model. It's a conceptual cartoon. We can add numbers to it. We can say how weak does this have to be, but I think that works. And it's a way to regenerate the roots themselves. Yep.
If you think about, say, quantifying the success or failure of different models and consider, say, the long-term erosion or entrainment or mass transport of what used to be continent to the lower mantle, do these buffer zones then really sort of switch from working, not working? Or is it more a gradual change? And then can you quantify how much better malls with crumpled zones do, say, compared to malls that just have light and strong zones?
You can, and that's what we did in the paper. I mean, you'd have to sort of read through it, and we tried to provide, and the paper by Misaki tried to provide objective measures on that. It's not a hard conclusion that you're going to get, because there's more than one way to preserve a craton is the conclusion you come to. That's right. Is it the primary one in terms of the trade-off? Well, let me just give you my conclusions. No, I don't think so. I can't say that.
70-30?
50-50. Here's why I can't say that. I didn't show you the 300. I showed you a lot of things that don't work, and I wanted to show you things that don't work to get us thinking. But we can come back and think about what does work. I missed my slides. Anyway, I'll come back to it. We were also thinking about instability. And when I showed you models that don't work, I wanted to for a reason. Complete root removal was recognized. North China cratons, xenoliths in the Ordovician indicate mantle lithosphere, typically cratonic. Later basalts indicate different sources, constraints, timing. This is from a paper by Foley. This is from the original paper by Menzies when I noted North China. It looks like North China was cratonic for a long period of time based on xenoliths that come up, similar to what we saw early on. And then later xenoliths, Nature Was Kind, a later volcanic event, actually showed none of that root material. So we have to deal with something potentially going unstable as well. And that's a new twist in cratonology. And the discussions Jim and I were having, we're trying to get to that same thing. If it is the viscosity, if you know the number, then we can say, okay, if you are rehydrating it, how much do you have to rehydrate it if you think that's what happened in North China? I don't know if that's the answer or not. But that's, again, why I think the exercise is useful. Here's Thorsten's question. Here are the models that I think work. You can do it with dry viscosity and a critical thickness to prevent localized deformation. You cannot let the root fail, and you can have these mobile buffers. All right, so maybe this is your question. If you make the buffers weak enough, this one and this one, I can't discriminate between their effectiveness. And within reason of what mobile belt weakness would be, I can't rule them out just based on that. Does that?
The reason I'm asking is also the chicken and egg, right?
Yeah.
When this whole thing started, we were making strong things first, and then the squishies and all that.
Yeah. The models, I think I see where you're going. The models I have do not address that question. In fact, they purposefully bypass it. They do, I hope, and this is what we're talking about, maybe set up the next level of models that you would have to do to address that question, which do involve issues of formation, and that's where I am going. How did the material form? Because that would be very different in terms of the predictions. The chicken and egg, which came first. I put them all there. That's not the real world. And of course, you're not getting down on me that because you know a model is a simplified representation. Yes. No, I think it's good. Yes.
Think about Dietz's cartoon where you have a mobile stress belt, mobile stress buffer, belt stress buffer, MBSB. It gets thin over time. So you see models going from regimes where you go from stability to instability as the shear stresses increase as that mobile belt stress buffer gets thin.
If you actually, completely eat it away, eventually, you will go unstable if you lose it. And that's an interesting implication. Why do I say it's an interesting implication?
Adrian, on a related
Yeah.
note, so you're saying one possibility is thickness. So say the cratons start off at 250 kilometers thick at the very beginning, but then over 2 billion years, could it be thermally
Yes.
thinned? And then what would that do? What
Yes.
prevents it from being thermally thinned?
Yes, and I don't know, but we'll get there. So I said inherently we're thinking instability when we think stability. If this is what we go with, right, and I say these work, you say, okay, to go unstable, maybe you have to rehydrate. Or, Sinti, man, you guys are good foils for me, or you progressively thin. Or maybe the yield stress is a hydration one. I don't know. I put a question mark there. I don't understand that as well. Or, Mark, man, I got 3 good foils. You lose the buffer. Thin from below. Completely not planned, right? Okay. What if that does happen? What if you couldn't progressively thin it from below? Thermal erosion, eat it away. Maybe progressively lower its thickness, slowly, not catastrophically. Can you hit some critical point where now it's not thick enough to prevent fracture? Don Turcotte would agree there's going to be some limit. Can you do it that way? Maybe. Is that wacky? Only insofar as you might think Stephen Foley is wacky. He's actually suggested this. For those of you who haven't read this paper, rejuvenation and erosion of cratonic lithosphere. In fact, the suggestion is, and we can talk about the evidence for this, that you can have weakening and erosion from below. progressively. Cryonic lithosphere is more susceptible to chemical alterations than is generally assumed, especially at deeper levels. Maybe you are eroding it. Maybe it goes below a critical level, and if you come near a subduction zone, maybe then it fails. There's a prediction there. You shouldn't see cratons below some critical thickness. Seismologists, if you want to test this out, I can give you the numbers.
Can I say on that? I mean, critical to this is actually it's the depth of transport of material that goes in. So it needs a lot of melt to generate. So it's too thick.
Right.
If you can generate too much. So is there a threshold?
I don't know. You're exactly right. If you think this is something worth exploring, you would have to do a new set of models akin to which I have not done at all. I've done nothing on this. It's just conceptual. But if you think it's a good idea worth exploring, yeah, you would do exactly what Cinti said. Ask yourself, is that possible? I don't know the answer to that. I don't.
What's all these physical pictures behind this fairly creative cartoon?
Metasomatism?
It's localized melting. I'll probably address some of that.
Okay, good. Yeah. What about this other one? Yeah.
Today we see that the cratonic, also the size are different, so maybe also the thickness of the different cratons are different.
Yes.
So
yes.
this implies that the smaller cratons, they are less resisting than the larger structure.
If they come into a subduction zone, yeah, it's a prediction.
So
yeah.
With time, I don't know if the size of cratonic area, how they change, if we have an idea. So
That would be, I don't know the answer to that. It's a great question.
Let's say that as the cratons becomes thinner and thinner, as size, let's say, they will also become destroyed easily.
Yes. I don't say that's the way the world works, but that's what, if you take this avenue, that would be your prediction, yeah. One other thing, if you want a little modeling tutorial, you want your models to predict things. Yeah. Yes. Yeah, Shiji.
I guess, I didn't mean to be a criticism.
No, it's fine.
So I feel like, so if I'm a geologist or I'm a geochemist and I want to test all the scenarios you propose there, where should I start?
Well,
Okay, sea level change or some kind of sedimentation, certain kind of volcanism.
yeah, no, if you want to test which one provides stability or it provides instability. In terms of what provides the stability, I have to tell you, I've thought about this. I couldn't rule out either end member. I haven't thought about it. Maybe other people can as to what the predictions would imply. The one that comes into it is, I think, the instability. That's where you have a little bit more test.
Yeah, I guess stability, you probably nothing happens. So then,
yeah, well, exactly. Yeah, yeah.
But if something happens, then let's say instability. So that actually probably provide a way to test your instability.
Yes.
So should I, let's say North China crater, okay, right, it's been gone, and maybe warming crater is gone, and so what should we do in terms of testing what actually caused it?
That's actually what I want us to talk about. I don't know, Shiji. I'm actually setting us up for that discussion. I don't know.
Well, it's wet. It's still there.
Excuse me. I'm wondering if the model design actual production.
Let me just go through the other prediction, the other one for instability, and then what I wanted us is to compare the two. How do we test that? The other option is the one Mark said, that it's not a thinning from below, that maybe you don't have this buffer zone. Then we look at North China, and this is a plate reconstruction where we have the subduction zone. I actually did show this. I told people I showed this in China, and then people said, why are you showing Japan next to China? But that's the way it was. There it was. You had the subduction zone. You had the slab. You had recall Rick's discussion of Cap Val, the Cape Fold Belt. You have no Cape Fold Belt. You have all the conditions for thinning out the buffer, if you think that that's what's going on, to allow for this to go unstable. Now, this is the issue, Shiji. Statistics of small numbers. That's not me. That's the Earth. That's the Earth. If this is right, give it time, other ones are going to go unstable. Wyoming, flat subduction, slab moving through at the base, eating away the base. That one suggests more that thickness, critical thickness one. Maybe both can happen. The Earth doesn't like to be pigeonholed, just, I don't know, that's an obvious thing. It doesn't have to be one or the other. It's a possibility. I can't, right now, I mean, maybe people can help me. I can't discriminate. There are some implications that we can do with other models. There's something, a bit bigger issue I want to leave us with here. If, in terms of sort of testing these ideas out, what's causing it, what's going on. That's North China Craton. This is a Dali painting showing clock and time issues. The instability in North China is relatively recent, and it happened fast. And it brings up a question. I don't know the answer to this, and it actually somewhat relates to recycling. Is this actually indicating us that actually it's only recently the Earth has sort of set itself up for instability? Or has this been going on in the past, and maybe we had some roots that we've lost? I don't know the answer.
Combining your talk and Rick's, right? It seems like the geochemists are more confident to talk about how continents are made. Geodynamicists have a lot of ideas on how they're destroyed or not destroyed. Is that sort of a good complementary thing? Or?
You know, in a word, it used to be. In sort of the era where students are thinking about new directions to go, when I was saying, you know, what model has been played out, no. What actually we should get to, and this is one of the implications, if it is thickness, or if it is mobile belts, all of that is pushing me personally to say, all this modeling, that was great, but here's what it's suggesting. The issue is, completely, formation. That's what needs to be addressed. That the stability comes somehow from the formation process. Now, I could be wrong on that too. I don't know. Does that answer your question? Oh.
But Adrian, what are the statistics of, so you've got plates floating around the surface of the Earth. You've got, some of them have cratons in the middle, some of them might have a craton on the edge. I guess the point is how often are you going to get a craton put into a place like the South China or the North China craton, like this, where it's right up against the subduction zone that ends up turning into a back arc basin and eroding the whole side that's in the active part of the margin?
Excellent question. This actually maybe comes back to...
Could you just play the statistics where that only happens 1 in 100 times in a continental margin evolution?
You can do this game, and you can play the statistics of small number games, and I can do it in a modeling sense, too, and you can do it on a 3D sphere modeling sense. You put it on, and you just see what happens over time, and you build up the statistics. If you stick with the number of cratons we have today, it's small, and maybe it only happens every now and then. If you think there were other ones around before, it's different. Now, back to Shiji's question, right? Here's the way you might really want to do this, related to Rick's question. If we could do plate reconstructions back past 250 million years, and for example, if you saw there's a craton on the edge of Australia, for example, without a buffer belt. If you saw in a plate reconstruction it was near this setting, in a subduction zone setting, and it's still there, you say that model's wrong. And I have no problem with you, by the way. I also tell students, never fall in love with a model. They might be wrong. That you could do it. I don't know how to do plate reconstructions that far back.
Well, there's a part of the top wall that's in Antarctica, and where it rifted off, it doesn't look like it destroyed the craton in the process. I mean, it transferred part of the top wall, and it went with Antarctica when it left.
Okay, well, that's interesting, but do you see that the rift actually extended into the craton itself, that it went unstable? Kent's question, that it's not just longevity.
Like this.
It doesn't? Okay, well then that might be the evidence we're looking for. It's worth pursuing, I hope.
I have a question about your mobile belts, because you need some sort of subduction to create a mobile belt, don't you? And therefore you have to have an Archean craton exposed. So how does that exactly work?
That was with the Dietz model. That's the one I imagine that generally subduction starts a little bit offshore. And Dietz's model, now maybe some people don't like this as subduction initiation, involved passive margin sedimentation. The sediments form, they're weak, and then that actually forms your mobile belt.
Yeah, but you have to accrete it still.
Or you form an island arc off the edge.
Right.
And then when you slam in, you have the island arc itself that's accreting on. So if we go like the Shengor and Shengor models for the formation of, the Eurasian craton, where you have all these mobile belts coming on the side.
But I'm just saying the mobile belts themselves are the same process. Aren't they sort of fundamentally the same process that you're appealing to destroy the craton?
Yes. But you have to form them then offshore, not directly.
Yeah, but you still have to get them onto the craton.
Yeah. You form in a back arc setting. You form the weak mobile belt, and then you slam it together, maybe with two cratons in between. That's the way I can imagine that working. Maybe you think that doesn't work that way. I don't know, but that's why I showed that Dietz model. That's the issue.
Well, I think that what we have to do is look for some examples of that very situation. If you can find some examples, for instance, Japan and the Sea of Japan behind it, would that be an example?
That's the one I know of, yeah.
Sea of Japan behind it is not an example because that's not Archean. Archean is about south of 42 north. So Beijing is Archean. So the majority is not Archean.
I think we kind of naturally went into questions, so.
No, we were in questions the whole time. That's what I want, yeah. Anyone?
I was just wondering, can you model this? If you have a shallow subduction, like 100 kilometers, could oceanic shallow subduction mechanically plow off some Archean lithosphere?
Well, Cinti and I wrote a paper.
Mechanically break it off.
Cinti and I wrote a paper that said it could, so I guess I got to stick with that.
Oh, good.
Yeah. 100 kilometers you can remove that way? Yeah.
How much lateral, like how far in? Just keep going if the thing can...
Ask Thorsten that question. That's not what I...
I'm assuming if you can move 500 kilometers, you just go...
How far can flat subduction go is the question.
Just maybe a couple more questions. Maybe some students might want to ask some questions.
Yes, thank you. And so I want to raise your attention to a recent paper by in Nature about the rheology of mantle rocks, about the water effect. So actually in that paper that it has been said, from 1 ppm to 1,000 ppm, the viscous contrast by water effect is just one order, just 10. So actually in your model, you need 1,000 with viscous contrast.
If that's the only thing at work, yes, that's right. Which is, again, why I wanted to think. I actually think, I'll tip my hat, water on its own for viscosity is not enough.
And because what kind of rheology do you use? Is Newtonian rheology or?
The models, I mean, we went through different parameters. We went through Newtonian viscosity, non-Newtonian viscosity, so power law rheology of into the 3. When you do the viscosity argument, you're getting an effective viscosity. So if you have non-Newtonian rheology, you can weaken the material as well. That's one way to do it. Maybe you can get lower than that threshold value. So we tried both.
Yeah.
Maybe the bigger issue is how we're dealing with the ductile shear zones, those faults. That's through a plastic formulation. Now we've done it 2 ways. Mm-hmm. One way is a von Mises type of approach with a depth dependence. But we also did add a history dependence in there, which says once the material fails, and it's arbitrary parameter, it can actually stay weak for some period of time. Okay. And that's why I mentioned those fault zone models on the edge, if you actually keep it there. Greg Hurt's coming to talk about this rheology. What we're modeling is, and this will tip you off as to why I think this is one of the bigger uncertainties, is what rheologists call the semi-brittle regime. Yeah. Where we don't exactly know what's going on, but I'm using their values. But the microphysics of what's going on there, I think we don't completely understand.
Yeah, because I used Newtonian rheology, I found that it's just really the factor of 10, and maybe it's a factor of 10 in non-Newtonian rheology. It's similar to a factor of 1,100 in Newtonian rheology.
Right, and that's not a surprise, and I think we're consistent in that, and that actually goes back. Uli Christensen looked at this in another context as well, that you can actually dummy the effects of non-Newtonian rheology by lowering the activation energy in Newtonian rheology, yes.
And also I found in non-Newtonian rheology, the root cycles is not, I mean, the stabilities don't really depend on the root cycles. Not so much like in Newtonian rheology.
Well, that's interesting, because then we should talk about that, because then we're disagreeing a little bit.
Okay.
No, in the same way, disagreement is good, problems are good, right? Yeah,
this could be a research topic.